Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. I'm going to be looking at the shoot 'em up construction kit. In the previous episode, we looked at how to extract the background data, including the maps and blocks and characters. In this episode, we're going to look at how to extract the level data, what to display and when to display it and for how long and how the scrolling works. So in SEUCK we have 22 levels from 1 to 22, and each level can have a type of still or push or scroll with a certain speed. We can say for still screens where the screen is actually displayed from within this large virtual scrolling map. This is important because the levels tie into enemy attack waves. This is where enemy animations are chosen and then placed in this very large virtual scrolling map. So from the level data we have a notion of static screens and scrolling screens, whether or not they're forced scroll or pushed scroll, which is where the player goes to the top of the player area and then forces the scroll, pushes the scroll. But we can choose a particular point in the map from a rough position and then a fine position. The fine position is where you adjust it on a pixel level for the scroll, and then we can see where the enemy animations are placed, and the trigger point for these enemy animations coming on the screen is actually that position in the map, which corresponds to where the positions are in the area that you are choosing for your individual levels, whether or not they're a static screen or a scroll screen. So to make it easier what I'm talking about when I'm looking at still screens, I'm going to choose one of these blocks that is easily recognizable, and I'm going to edit what looks like identical screens. So we have this screen here, the first level. The second level is this second screen, which looks identical at the moment, but I'm going to be adding what is a capacitor. These red circular looking components are actually disk capacitors. So the first level has none, and then the second level has 1, the third level has 2, and the fourth level has 3, for example. This makes it very obvious now that these different screens with the different enemy animation placements will be triggered at different times. For the first level, the still screen is displayed for 15 seconds, the second level, the still screen is displayed for 8 seconds, and then the third level, the still screen is displayed for 7 seconds. I make sure that the first level is highlighted so that when I go to test game and choose cheat mode, the cheat mode starts on the level that you have highlighted in the editor. So this is the first screen. The second screen will come along soon, and there we go, there's the capacitor, and it indicates that we are actually showing the second screen that looks almost identical from the map, and then this is the third level with the 2 capacitors that come along. This is the third screen and this is the fourth screen section that was identified in the level data from the virtual scrolling map. And then this level goes into a push scroll portion of the game where the player walks up to the top of the level and then pushes, and then this pushes the scroll down. So we'll save all of that data because we want to use that for an example later on to show that the code works for how the level controlling code works. So we'll just save all of this. Because I'm using virtual device traps, the save is actually quite nice and quick. Like in the previous video, I'm going to be saving a base version of the data which will be used to do the initial comparisons against using the binary difference tool. Now let's edit the first level so that we can try and identify changed data within the all data file. Going back to the documentation, we did this in the previous video, which was how to find the characters in the blocks and the maps. Now this is the levels portion. This is going to get a little bit complicated because the data is a little bit more complicated, I think, than the map data. With the map data, the characters and the blocks and the map layout used quite large contiguous blocks of memory, whereas the level data is going to get more complicated because the level data contains more flags and more offsets, but it's in a tightly packed data format. So we need to change as many parameters as we can for the first level to make the data, the binary data when it's saved out, as obvious as possible. When we do a file comparison, we want this to be as different as possible. So instead of loop, I'm going to change that to, say, for example, a redraw or continue. It doesn't really matter. These are the three end of level configurations that you can apply. I'm going to change that to, say, for example, be a still screen, and then I can change the duration just for the first level. We don't want to get confused with different data. And then I'm going to change the position of the level in the level map. So although it's difficult to see, I'm scrolling up through the virtual map, but because the virtual map is all filled with the same block, there's nothing different on the screen. But I'm holding down fire and pushing up on the joystick, which scrolls up through the virtual map. Then I'm going to save all of that data. I noticed actually in the emulator that when I type really quickly, it introduces incorrect characters even though I'm not pressing those keys. It might be a key rollover issue or something like that, but it seems to only happen in SEUCK, so there we go. SEUCK might have a problem with its keyboard matrix read, maybe, I don't know, I'll have to have a look at that maybe later on if I'm interested too. So that's all of the data for changing only the first level. Here's the two files that were saved out. Let's do a comparison with this lovely Beyond Compare tool, which is fantastic for having a good view about what has changed in a file, especially for binary views. I quite like it. And let's go down through memory to see what has changed. I don't think it's that difference because it was only 1 byte. There's only 1 byte changed here too, so I don't think it's that difference either. We see these occasional bytes being changed within the editor. I think it might be a menu state or something like that. It's nothing really too interesting, I don't think. Don't forget that the save all data file includes most of the editor's data as well for text, messages and screens and all sorts of stuff. So we can see that here. Although there's quite a lot of differences, it looks like differences in terms of what is being displayed on screen, which is not interesting to us. This seems like a string working buffer or something like that. So this is text. I don't think this is game configuration data. It's not really important to us. What is important to us, I think, is this changed data here. Starting at AE92 file offset, we have what looks like a few bytes changed. So we need to, I think this is the portion of data that's important for the level data. So we should try and start to make sense of what these bytes mean. Now I think that the bytes for the first level have been identified, let's try and change individual pieces of data and to see how these bytes actually do change. Let's go back to the level parameters menu. Now we have the base values here. Those are the 7 hex bytes for the base file, and then having changed everything for level 1 that I could think of changing, those were how the new 7 hex bytes have changed. So we have quite a lot of significant change there. But to better understand this, we need to change small pieces of data. Now I think that 5 corresponds to the 5 seconds of duration, for example, but to be able to test this we need to incrementally or make small changes and then to study the changes in terms of bytes in the saved file. This is the same kind of checking that we did before. with trying to find the characters, the blocks, the colors, and the map layout. The end of level can be changed from continue to redraw, for example, and then using the storage menu again, save all data and give it a sensible file name. For example, level 1 redraw. Looking at the differences between those two files, specifically in the area that was just identified earlier on. So these are the new bytes. When trying to reverse engineer file data like this, it's always a good idea to keep a lot of notes about what's going on and to make these changes slowly and consistently so that it reduces any chances for misunderstanding. Here we can see that the only thing that has changed in terms of the byte data is that the 80 has changed to a 00. As I find out what each byte offset does, I'm adding some notes for what I think they are. So this is byte offset 0, this is byte offset 1, 2, 3, 4, 5, and 6, so 0 to 6 in total, which is 7 bytes. As I noted earlier on, I think byte offset number 4 is the duration in terms of the number of seconds that the still screen is active for, being drawn for. I think byte offset 6 is the redraw loop or continue option, because that's what was changed between the base version, the level 1 file, and the level 1 redraw. Byte offset 6 might be the type, for example, so if instead of the still screen it is changed to, for example, scroll speed 2, and then saved as all data, again with a sensible file name, and then the other type is push scroll. There is still, scroll, and push in here in SEUCK, so we change that variation as well. The speed is also a variation for the level parameters, so let's change that to be push, scroll, and speed 1 instead of what it was just now, which is push, scroll, and speed 2. Again, save it as a sensible file name. The other parameter for the levels are the screen positions in the map, or the start and end scroll positions in the overall virtual map data, which we'll have a look at presently. But first of all, let's see if we can map out some of these values first. For the change to scroll with speed 2. So we look at the binary data in the right place, and we pull out these values, these hex bytes, from the correct start address for where the level data starts. Oh, whoops, I copied the wrong one there. That's redraw. This is the scroll2 file, so that's the change for introducing scroll2 as a parameter rather than the still screen type. So let's put that there. There we are. We can see here that when it's using scroll2 instead of static, then the last bit, in other words, the hex value 80 seems to be introduced. However, to really be sure, we might need to look at some other data, I think. Adding some extra notes for clarity for what the changes actually were. This helps with being able to deduce what the byte values actually mean. And don't forget, being a computer, the byte values can just be using a combination of bits, or maybe groups of bits, can be values, binary values, and then other bits, either in isolation or in groups, can be other values, or they can be individual bit values for flags. So we have to keep this in mind when we are looking to reverse engineer this data. Let's have a look for the difference between the push scroll speed 2 and scroll speed 2. Let's just double check that. On the right hand side is the push 2 file, which is the change 2 using push with scroll speed 2. So the value C is actually 2 bits. We can validate that. So 81 in hex is this in binary. It's 1 0 0 0 0 0 1. But C1 is actually 1 1 0 0 0 0 0 1. And this is where we look at bit patterns rather than just values in a byte, because this byte seems to have different bit flags encoded inside it. The most significant largest bit is on the left, and the least significant bit, the smallest bit, is on the right here. But that's just by convention when writing out a binary number. One thing that does come to mind when I'm looking at this again after such a long time is whether or not there's any extra movement types that might be included in the code but aren't included in the finished editor. That might be something, right? But I haven't ever checked, to be honest. I mean, looking at these bit values, right? There's 0 for still. There's 1 0 for scroll, and then 1 1 for push. Okay, so the last bit number 7, which in hex is 8 0, could be the scroll flag, and the other bit can indicate whether or not it's push scrolling or not push scrolling. That's a possibility. That's probably how the code is structured, to be honest. There would never be a still screen with push, for example. I mean, a still screen with push doesn't make any sense, right? Because push is what happens when the player character gets to the top of the screen and pushes against the top of their player limitations. The player limitations can actually have the player in a smaller area just than the full screen, of course. I mean, the player limitations can have a small box in the middle of the screen or at the top or the bottom, wherever. If the player is pushing up against the top of their limitations rectangle, then that causes a push scroll. So I think this lower bit is actually the scroll speed. In other words, speed 1 is bit 0 and speed 2 is bit 1 being set, or bit 0 being set to 1. I think that's the way it is encoded in this. It makes sense, right? Just adding these insights into the notes file, just so we can see what's going on. And so all of this data doesn't need to be kept inside my memory because my memory is terrible these days. The other bytes in the level structure would then logically be the start and end positions for the blocks in the large scrolling virtual map. And the virtual map being so large vertically, I think it would need more than 1 byte, because each byte can contain values from 0 to 255. So to have numbers bigger than 255, you need to go into 16-bit or 2-byte values rather than just 1 byte value, which just has 8 bits. But that needs to be completely checked. Let's just double check that. Because not only is it an important part of which static screen is displayed, it's an important part for how the scrolling map area sections, whatever you want to call them, actually work. I'm saving a snapshot here for demo 1 because I've just loaded the demo 1 example game, because this is going to make it easier to see when I'm scrolling the level map parameters for each kind of screen or each scrollable section within the game. So again, this is the base data. I'm not going to change anything from the base demo 1 file. Then go back to editing the levels. This is what the game looks like. It's this one, right? The first demo game. We can see it has a scrolling section. It then goes to a static screen where the boss comes along. A big enemy, basically, right? This big flying thing, whatever it is. This is a static screen, which is static for a certain number of seconds. And then it continues on scrolling. Right, so that's what it looks like in terms of the level structure at the beginning of the game. So that's level 2. Level 1. I'm setting the first level to be still with, what shall I choose? Redraw. And the second level is still, but I don't want it to stay on the screen for that long. I'm also setting it to be redraw, setting the third level to be still and also a few seconds long, and then setting that to be loop. That completely changes the structure of the level, right? So now I'm changing the screen position for each static screen. So the first level is the very first section of the map, right down at the bottom. I could not scroll any further downwards than that. The next level is around about there, and then the third level, I'm going to scroll it up a little bit. So this is what it should look like. Oops. When I test the game. The first static screen, then the boss screen, and then the boss with this static screen here, for example. You might notice in the transition between these different screens as well that the color data takes some time to get updated. This is one of the things also that I want to fix by recoding this from scratch, is by having faster routines that have less color lag. So let's save that as all data. 3 static screen levels that cycle around, right? Then of course let's do another comparison. I'm actually seeing quite a lot of binary differences, more than I expect. I have a feeling that that's because when I saved out all data, I had already executed the game. And because I had run the game, when it runs in the editor, probably updates an awful lot of memory. things like sort tables and animation tables and all sorts of extra data like that, which is going to make it would have made it more difficult to see, but I had already identified the area in memory that I was looking at, AE92, right? But this time it is 3 times 7 bytes that we want to pull out of the file here. So we'll just pull out a decent amount of data, and then we'll chop it up and then see what we get when we try and decode this. So 1, 2, 3, 4, 5, 6, 7 bytes. There we go. 1, 2, 3, 4, 5, 6, 7 bytes again. Bunk, bunk, bunk. So let's see if we can decode what we get. So we have the first level, which seems to start at the beginning of the map data all the way down at the bottom. So we have 3 static screens to begin with. We know they're static screens because byte offset 4 is the duration. So we can see there the times that the static screens are actually visible are 2, 3, and 4 seconds respectively. That's fine. We can see that we have still screen, followed by, or rather redraw, redraw, and then loop, which is what we have there. But we have, if we have a look at the types, which is byte 5, we have still screen, 3 still screens, right? Because that's byte 0, and there's no scrolling speed set up either. So again, bytes 0 and 1 and bytes offset 2 and 3 look like the start position and end position, right? Because I scrolled down right to the bottom of the map and had the first static screen there, and then I scrolled up a bit, and the level 2 static screen, or still screen rather, has an offset which is higher up the virtual map. But we can double check that just by scrolling the first level still screen, the static screen, up 1 block. That's what we did there, and we can save that all data as up 1 block. Basically just shift the screen up 1 block. Then if we have a look at the differences between those 2 files, between the static screen, the still screens rather, and the up 1 block still screen, let's just do a double check on that. Go down to the correct bytes offset within the file, and yes, there we go. So instead of 0, 0, 0, 0, we have 0, 1, 0, 0, and 0, 1, 0, 0. So it's a little endian number, which makes sense. The 6502 is little endian, meaning that the first byte is the least significant byte, and then the more significant bytes are after that in memory. Low and high byte ordering basically for a 16-bit value, which is 2 bytes long, because each byte is 8 bits in size. So a 16-bit number, which represents a number from 0 to 665,535 in decimal, is the low byte, high byte ordering. So the virtual map, the whole map, scrollable map area, is actually very tall. So if we edit the level parameters to change the scrolling level end up by 1, right? So the end scroll, so the scrolling levels in terms of the map area have a start and end position where they start scrolling and finish scrolling, obviously. I've just changed level 5, which was a scrolling level, so that the end of that level is scrolling 1 extra block vertically. So then let's have a look at what numbers changed there. And we can see instead of BA, it's now BB. So the start is at 6, 0 with 0, 0, so flipping around the byte ordering because it's low byte, high byte order. We want it high byte, low byte. So it's 6000 in hex is the start position. And then of course BA with 1 added to it is BB, which is kind of what we expect. So I have a crazy idea. Well, first of all, we need to double check that that's the correct file offset. So level 5 is actually in starting with 0 numbering is level 4, level 0, level 1, level 2, level 3, level 4. So we have 7 bytes in total, so we have 4 times 7, which is 1 C byte. So 1 C bytes plus what was the start address of the level data in memory? Can anyone remember what the hex number was? It's AE92. So 1C plus AE92 gives us AEAE, which is where we were looking just now. So this is the start of level 5, which in 0 numbering is level 4. And this is the low byte, high byte, low byte, high byte of the start and end of memory. So we can see that it has been incremented by 1. I think that that tells me with a good degree of certainty that it is the start position and end position in low byte, high byte format for the block line in the virtual scrollable map area. And that's what those numbers mean. I wonder what the maximum number range is going to be. We can check that out in a minute. It's important to know the byte ordering for how the numbers larger than 1 byte, larger than 8 bits are laid out in memory, because you need to know this byte ordering to correctly pass the numeric value that you're looking for, right? So if I scroll the end of level 5 now all the way to the end of the virtual map, the whole map, in other words, scroll it all the way to the start. Don't forget from the previous video that the map is from bottom up. There we go. So that is the very top extent of the whole map. So if we save that, we're now going to get the maximum extent for the number right at the end of where the end position for the map can actually scroll to. So if we have a look at that binary difference now, there we go. So it's now using obviously 2 bytes, so we can definitely see that it is a 2 byte number, and because it's in low byte, high byte order, we'll flip the bytes around, and that means that it is 1 FB. So there are a maximum of 1 FB block rows within the full map. So we take the number of block rows, multiply that by 5 characters, which gives that many character rows, divided by 25 characters for a full screen, and we get 101, which is basically, we're probably 1 off, but that's basically 100 screens of scrollable, visible map data. Because each block is 5 by 5 characters, so that's why we take the number of block rows and then multiply that by 5, because a block is 5 characters tall and 5 characters wide. So all of that data that we have managed to study can now go in the documentation file. We now have enough data to be able to write the code. Of course, the code has already been written, and you can download the full game engine already from my GitHub link, and I put the link to the GitHub in the video description, of course, as well as within the this debugging text file, which is also in my GitHub source repository. So that static screen file that I saved out earlier on is then loaded as with a level properties label. And this is all of the nice information that was discovered, just formatted and put inside the scroller data.a source file. Now, level properties, the label is actually accessed by the level control source file. Don't forget that we need to adjust the location not for the file offset, but actually the offset, or rather the address of the data actually in memory. So we take AE92, subtract the file header length, and then add on an offset of 900 in hex, like we did for the characters and background data, basically all of the map blocks, characters, all of the color information. So that starts at memory address B776. This data was a little bit more complicated because it has those bit values encoded within the byte. But we can see here that the level properties label is mostly referenced by the level control.a file. Level control.a is the source file that contains the routines that deal with starting the game, deciding which sections of the map to render, either as still screens, static screens with a number of seconds of delay, or where the game starts and stops scrolling and with what speed, and also deals with enemy attack waves. But we'll look at enemy attack waves and animations in the next coming videos. So there's some logic to deal with parsing the level properties data and then just telling the game engine what you want to render and for how long. Basically, it's not terribly difficult code. It just has quite a few different states, that's all. It also needs to know how to set up the difference between a push scroll and a normal forced scroll. So it handles that too. And it has a notion of being able to detect when the scroll reaches a certain endpoint, so that it can then decide what to do when it wants to transition to the next level. You can see here the level setup next level function takes all of this data and then decides what it wants to do with it. It resets some internal counters, it resets the velocity and stuff like that for what the game logic needs to do to be able to interface between the level control and the actual map, draw or scroll routines. When we run this code, then we can see that with that data that was edited, it displays the screens in the expected order. If I change this to be normal borders and move this screen down there, we can compare that with what the actual SEUCK game engine wants to display. And we can just see that it does display the same data. So we'll put these versions side by side. As always, the original SEUCK is on the left and the new code is on the right. Of course, it helps that if I use the correct data, right? So there we go. There's the static screens, all data being loaded. Test the game, proper test. We see it starts with that screen. It then renders the boss screen, and then it flips to that screen. Draws that screen. If I try and reset the game side by side, there you go. You can see that the delay between the two is identical. So the screens should be rendering practically identically. Which they certainly seem to be. And there we have it. That's the end of trying to parse this level data. The next video we're going to be getting into interesting things like sprites and maybe how the animations are set out in the memory. Firing is a little bit more difficult because it deals with spawning extra sprites, and attack waves are then even more difficult after that. The reverse engineering effort definitely seems very worthwhile to me. It's very satisfying to see that people take the reverse engineered code and then we get extra games like, say for example, the best SEUCK game ever in my opinion. With all of these enhancements, it hardly feels like a SEUCK anymore. Great, much better than a lot of non-SEUCK shooters, thumbs up. So Richard Bayliss and Alf did this game with the reverse engineered code and produced this version here. So because all of the source code is available, it makes it very easy to expand the game way beyond what the original SEUCK was capable of doing. So this game actually adds things like pickups, which enhance the ship's speed. It enhances the ship's bullets. There's extra little title screens with really cool music as well. Actually, I think one of the pickups as well, there we go, it adds an extra drone. You can speed up the drone, you can activate the drone, you get 3 times laser with the drone, all sorts. And then you can have a smart bomb as well, so you flash the screen, you press it, the screen border flashes, you press space apparently, and the enemies on the screen get killed with the smart bomb. So you can greatly expand what looked like the old SEUCK games and make them a lot better looking. So this has a nice title screen with a scrolling message, and actually there's a high score table as well. You have this intermission screen, like the get ready screen with cool music, and the score panel is vastly changed. The game has music rather than sound effects. And these stars are the pickups. So there's a power up that you can pick up there. And the first one enhances your ship's speed. There we go, the ship is moving a lot quicker now. I'm not very good at this game, to be honest. I'm trying to get to the part where another pickup is able to be found. Hopefully soon. There we go, there's a star on the right hand side. So if I pick that up, now the ship graphic changes, I think, and then now I've got double lasers. And then if I try and pick up this one, there we go, the ship graphic changes again to indicate that I've got triple lasers now, and I think they do more damage. Oops, I shot the hospital ship, which you're not meant to do, I think, or the ambulance spaceship or whatever it is, and you lose a life when you do that. So oops the daisies. And then once you lose a life, your ship gets demoted all the way back down to its base configuration again. Let's see if I can play ahead to where you pick up enough power-ups to actually get the extra drone as well. So that is obviously a lot different to the standard SEUCK game. Hold on a second. So here I die, and then you get a game over screen, and then you get a high score entry screen as well, which is all cool, right? These are all features that were not available in the original SEUCK, so these are all added by having all of the extra code. So here we go, and there's another power up, and now I've got an extra drone for my ship, so that now the drone can fire extra lasers as well. So this is definitely a feature that you would not have in the original SEUCK. This drone is actually a second player with slower speed, but it's been duplicated to be controlled by the same joystick, for example. So this drone adds a much extra needed feature, and you can have these like boss enemies with linked sprites as well. So if you kill one of the enemy sprites, it explodes all of the enemy sprites that are linked to it as well. So these were linked enemy graphics that were a feature added to the SEUCK Redux engine, basically, which is what I call this new source code, right? It's called the Redux engine. And there we go, I shot the ambulance spaceship again and lost a life. Whoops. So I think we'll leave this video there. We'll just go back to that last static screen data that was edited to add the extra capacitors at the beginning. Now just see if that data actually renders correctly, and it does. The updated code is on the right, the new code is on the right, the original SEUCK is on the left. We can see that the timing between those levels is correct. So I think we'll leave this video there. If you like these kind of crazy deep dive technical reverse engineering videos of Commodore 64 games, then please do consider liking or subscribing to this channel, and there are buttons down below specifically for that purpose, and that would be wicked great awesome. Thank you very much for watching, take care and have a great day wherever you are.